assume so. Okay. All right. Thanks, by the way, first for inviting me to speak at this kind of kickoff meeting. It's really exciting to be here. Briefly about myself. So I'm, like Pam said, research director with Infotech Research Group. We provide practical advice and research around a wide area of IT topics. I focus specifically on artificial intelligence and machine learning. I have quite a few years working in analytics and AI space. I actually started with artificial intelligence way back before social media, before big data. I won't tell you the date. I don't want to date myself. But that was way before, and so there was not enough demand. So I switched into data mining and business intelligence, and did that for many years on vendor side, so building these technologies. And about 10 years ago, I switched to client side and sort of led teams that used analytics technologies to deliver analytical applications at a few clients, including or a few organizations, including the most recent one was a global luxury hospitality brand. Now at Infotech, about 2 years ago, I did a full cycle or circle, pardon me, and went back to AI because that's obviously the technology that's taken the world by storm. And we wanted to write about it. We wanted to look at use cases, best practices, and help our members like you to get started with artificial intelligence and do it responsibly and ethically. So I cover the broad range from everything from strategy, use cases, through to execution, best practices, AI, ethics, and governance. All right, so today, and Pam, how much time do I have today? Because that will determine how fast or how slow I will go.
We assumed about a 45-minute window for your presentation.
Okay, perfect. All right, so let me just get started then with that and share it, put it in a full screen mode. Hopefully you can see it right now.
Yes, we can.
I assume. Okay. Thank you for confirming it, because once I switch it into full screen mode, I can't actually see any one of them. If anybody raising hand or putting anything in the comments, that's just how Microsoft Teams works. So demystifying artificial intelligence. Yeah, a lot is being written and said these days about AI. Everything from killer apps for your business to apps that will kill your job. And a lot of this is hype, right? So which I'm hoping explain in the next 40 minutes or so what AI truly is. And by the way, I think we may have some time for questions at the end, or you can always welcome to reach out to me after the presentation. In fact, many people talk about an AI revolution taking place, and maybe that's what's happening, like with, for example, the introduction of electricity in the late 1800s and early 1900s, which, by the way, took about 40 years to kind of penetrate all levels of society, the economy, the businesses, and also consumers. Now, interesting thing is, why is it happening right now? Why not, for example, 10 years ago or 20 years ago? Or AI as a field has been around actually for more than 60 years. The reason for it is a combination of multiple factors. One of them is availability of the cheap computing power and the powerful hardware that is really needed for AI to be successful. The other one is big data. From social media, but just all kinds of big data. And the third one is the algorithm themselves. And if you put these three components together, that's sort of what started the current revolution, where people say started sometime around maybe 2007. Okay, it's when we kind of started to leverage deep learning. And by the way, I'll be talking about it in a few minutes. But what is AI? When you ask people what they mean by that, many, at least until recently, used to go and say, well, it's kind of this, Alphago, the software artificial intelligence program from Google that defeated the South Korean champion of Go player. Lee Sedol. By the way, he's retired since then, and that's what happened about 4 years ago. I think time goes by very fast. And the reason people think about this, because if you're familiar with Go, if you read about this, is Go is a very complex strategical game. It actually has more moves, possible moves in the game, more moves than the number of atoms in the universe. And if you think about Go and compare it to, for example, chess, it's actually Go to chess is what chess is to checkers. Okay, it's a very complex game, and so if a machine could defeat a human, it must be smart and intelligence. Um, we'll kind of get back to this in a few minutes, but for us, I would suggest to truly understand what the current incarnation and what AI truly is. I recommend we go back in history at the beginning of the modern era of computing, which started just after the Second World War, when computers looked like something like this. So they were devices for crunching numbers, and some of them were actually humans, like in the movie Hidden Figures. And the field back then was known as the field of intelligent, quote unquote, machines. And that's what later became artificial intelligence. And back then, the researchers worked on all kinds of interesting problems like cybernetics and automata theory. But it all kind of started to change in around 1956, actually in 1956, in the summer of that year, when John McCarthy, then a young assistant professor in mathematics at Dartmouth College, decided to organize a study group and develop some ideas about thinking machines. And he was the one who kind of indigenously picked that name, artificial intelligence, for the project because it allowed him to achieve neutrality. He didn't want to take anybody's side, sort of not aligning with any particular discipline, which were in vogue back then. And so he kind of came up with this term, artificial intelligence. And in the process, what he also did is he unified researchers around this rather ambitious goal. So what did they decide to achieve, or what did they want to achieve back then in the summer of 1956? And this is a quote from the proposal they put together for that project. They thought that pretty much, every aspect of learning and human intelligence could be circumscribed so precisely that a machine can be made to simulate it. And they wanted to make an attempt to actually make machines to use language, form abstractions and concepts, and solve all kind of problems, and also to improve themselves. And that's actually a key word there, a key phrase, so keep it in mind, improving themselves. Okay. Because we'll be looking into this learning component shortly. All right. Now, interestingly, so it looks to me, and hopefully to you as well, that what they wanted to do is really simulate human intelligence. And interestingly enough, they also thought that a significant advance could be made if, they put together a small group of people. They were talking about 10 people and work on this for 2 months. It's quite interesting because now 60 years later, we are nowhere near that. But before we get to the current state of AI, let's just also take a look at what is human intelligence. Okay, what is that thing that they wanted to simulate using machines? Well, it's obviously a few things, and like they said, it's the ability to understand human language and things like navigate in the visual world, so locomotion and wayfinding. It's also the ability to manipulate objects, and it also things like learning and reasoning and understanding and grasping truth and separating truth from untruth and seeing relationships, considering meaning, separated facts from beliefs, and quite a few other things. And if you speak to cognitive scientists and AI scientists, they're actually, other disciplines, they actually seem to be also different kinds of intelligence. We talk about also emotion intelligence, for example. So this list, don't take it as exclusive, okay, or comprehensive. There are many other aspects of human intelligence that are not listed here. All right, so sounds probably a little bit more complex than what John McCarthy and his co-workers wanted to simulate. So how does that correlate or resonate or reflect, reflected in what, what we're experiencing right now, 60 years later? Well, on the left, we've got some of those, human cognitive intelligent capability or abilities. And I highlighted in blue the ones that sort of roughly correlate to the current state of AI. But let me just step back for a sec. So what we have on the left is what John McCarthy and his friends wanted to achieve to simulate human intelligence, and it's actually known as artificial general intelligence, or also good old-fashioned AI, and there are other terms as well. And that's what many people think about AI when you mention the phrase. This is kind of that science fiction point of view where we have some sort of intelligent being, not human, but being of some kind, that demonstrates things like a flexible understanding of the environment, some reasoning skills, and so on and so forth. This is what we want AI to be. This is what we envision it to be. That's a dream or a nightmare, depending on who you ask. So this is artificial general intelligence. This is our dream. What's on the right is actually what's taken the world by storm these days. This is the current state of AI. It's also known as applied artificial intelligence. Okay, and the other term for it is narrow AI, as opposed to general AI. And how does it compare? By the way, when I talk about AI, it's a complex field consisting of multiple subfields. There are things like natural language processing and speech technologies. There's obviously computer vision, or more than that, it encompasses things, anything related to image, face, video processing. These robotics and the foundation of technology, machine learning as well, that in fact powers or makes possible all other subcomponents and subfields of artificial intelligence. It's really the key technology, and in fact, all recent successes of the last, let's say, 10, 12, 15 years in natural language processing and in image processing, recognition, and so forth, they're all due to advances in machine learning. And we'll be talking about what machine learning is in detail in a few minutes, so bear with me. But how does that, oops, sorry, I went too far. But how does, again, the current state of AI, the narrow AI or applied AI, how does it compare to that, that vision and the dream? Well, it's actually, if you ask experts, they think that it's nowhere, the current state is nowhere near what we want it to be, not even close the level of intelligence displayed by a 6-year-old child. And in fact, it's really nothing more than mathematics on steroids or statistics on steroids, depends on who kind of you talk to. Because when the historical, so the dream approach was about simulating human intelligence. What we currently have is technologies that kind of mirror intelligence based on big data and historical patterns that surface from that big data. But again, I'm gonna go a little bit deeper into that in a few minutes. Now, remember that John McCarthy talked about making machines to improve themselves. And that's actually what machine learning is about, right? It's improving based on the data, the information we have available. And so that's, I said, it's a very important component of artificial intelligence stack or umbrella field. So what is machine learning? We need to kind of, peel the onion a bit and look into that as well. Well, here's the definition from Wikipedia. And I highlighted some of the key phrases here in blue color. What it really is, it's a use of statistical models, to kind of mine big data and automate or perform specific tasks without explicit instructions, but relying on the patterns in the data. The reason I kind of trying to parse this example, because what I really want to plant a seed in your mind that, again, there is no intelligence in artificial intelligence, none. It's all about mathematics and statistics, kind of on steroids. It's really about using using instructions, using code to solve specific tasks. Many of them are very narrow, relying on patterns in historical data. Okay. And if I boil it down even further, kind of to simplify it a little bit more, it's about big data and algorithms. And if you think about algorithms, they are like recipes, like cooking recipes, a set of instructions to solve a specific class of problems or perform a particular computation. And when it comes to that big data, by the way, we need typically lots and lots of it. That data, for the most part, needs to be labeled or annotated is another word. And that's because how machines learn from those labels that were created by typically humans. Just because about 70% of machine learning models in use are known as supervised. They learn from this label, and I walk you through the pros and explain what we mean by that. So they learn from these examples, from these labeled examples. At this point, you may be wondering, so what is the model? What are we talking about, these machine learning models? And what do I mean by that? Okay, let's me walk you through this example. Actually, a couple of examples. One of them will be trying to sell a house, and the other one will be about spam. How do we know which emails are spam? But let's talk about selling a house. Let's assume I have a house and I want to sell it. That's not my house, by the way, as much as I wish to. But how do I know how much I should be asking for it? Well, we kind of know, especially if you talk to real estate agents, and we know that there are quite a few factors that help us to figure that out. So one of those things is number of bedrooms, number of bathrooms. There's also square footage of the house typically correlates with the price. The larger it is, the more it costs. The neighborhood or the city it's in, and things like proximity to amenities and highways and good schools. And there may be other dimensional attributes as well. Okay. Are the factors. So what we're trying to do here, we're trying to reduce a fairly complex problem to some sort of a mathematical representation, which is like a formula I put on the slide. And what we don't know is how much any of those factors contribute to the house price. How do they kind of correlate to each other? It's these weights 1 through 4. So what we do to create a model or train a model, which is what the terminology is used, we kind of take this formula, which is our recipe, and we take a large data set with historical transactions where we have this information available for every house that has been sold. We know the number of bedrooms and bathrooms and square footage and so forth. We also know what the house sold for. So we run this model and train it on that historical data, and it learns those weights: weight 1, weight 2, weight 3, weight 4. Typically, in a specific probably location or geography, because a house in Toronto costs a lot less than, let's say, in California, or parts of California, let's say in San Francisco, or Bay Area. Um, so this is the process which is known as training a model on historical data. And then the model, that formula, once we've learned these weights, we actually now can take it and apply it to my house, which I'm trying to sell. And I can plug in my number of bedrooms, my number of bathrooms, my square footage, my neighborhood, and it will spit out a price, which should be hopefully, fairly accurate to how much, I can sell my house for. Okay. All right. Now, another example is spam. And let's say the example of spam, like Nigerian spam, you probably guys have seen. You must have received at least, one Nigerian spam email. There were a lot of I'm looking for spam systems now, kind of catch them. But interestingly enough, it's actually, and this Nigerian spam has been around for many, many years, and I was recently looking up. It's still a quote unquote big business opportunity for some, because it still costs about $700,000 per year in the United States, because there's still software that doesn't catch all that spam email, and there's still people who go for it. So what is Nigerian spam? It's somebody typically in another country, sends you an email. They say they have a fantastic investment opportunity, and all you need to do, and they want to share it with you, and all you need to do is disclose your banking information so they can temporarily park their money in your account. Now, let's say our spam filter, that's the word I was looking for, my apologies, missed that particular junk email. How do we actually make it aware, or how do we train that spam filter to recognize spam versus non-spam? Well, it turns out that if you look at which messages are spam, there are certain words and phrases that are kind of very predictive of that email being spam. It's phrases like free money or out of debt. So what do we do here? Like in the previous example, we actually assuming we have a data set of emails that label junk or not junk, and then we run a classification algorithm on those emails, and that algorithm, finds, which sort of the probabilities of words and phrases indicating a message being spam. Okay. Now, the two examples I just showed you is examples of supervised machine learning, again, where I use labels, and especially of regression, which was in the context of selling a house, and classification, which is here an example of spam filter. Now, there are other approaches, and there are other machine learning approaches and algorithms. There's also unsupervised, when we don't need these labeled examples. There's deep learning, which we'll be talking about in a few minutes. There's also reinforcement learning and semi-supervised. There's quite a few different approaches as well. I'm just took this supervised because, again, the majority of applications use that supervised approach. Now, here is another interesting case. Let's assume we've got pictures of cute animals, and we want to train machines to differentiate between cats and dogs, or just figure out, what is a cat, so it can actually label those images. How do we decide? We don't have words here. We don't have phrases. We don't have the formula, number of bedrooms and bathroom. We kind of have some ideas. There's a bit of a difference between the images, but there's a lot of similarities as well, because both look cute. They have a nose and two eyes and whiskers and a fur coat. Okay, the dog's ears are floppy, while the kittens are perky. But I don't think there's enough differentiation between. We kind of can't build a formula to distinguish dogs and cats. And this is actually where deep learning comes in, also known as neural networks, or lovingly called neural nets. What deep learning does, it's a technology based on sort of trying to simulate how the brain is organized. And what it does, it's really decomposes pictures into pixels, and then applies level of complex mathematics to figure out what makes a dog and what makes a cat. And for that, it needs hundreds of thousands of images of dogs and cats that have been labeled by humans. So it's supervised in that a way as well, although they are unsupervised deep learning approaches as well. At the end of that complex levels of mathematics, it typically presents a probability of this image, being a dog, a cat, or in this case, it's really an image of a boat. Okay. All right. So now let's take a look at the process itself. So again, we're still talking about supervised machine learning, and I kind of touched upon at the high level of how this training or building a model is performed, but let's now go a little bit deeper. There are two phases. One of them is what's above this dotted line, which is training, and then there's actual predicting. So once we've trained the model, we can use it to predict future outcomes or make decisions, for example. So what we do is we take some data, raw data, for training the model, and hopefully we've got some labels as well. Then we do some pre-processing, what's known as feature engineering or feature extraction, which by the way, by itself is a very complex and time intensive process. About 80% of machine learning is really nothing more than this feature engineering, data engineering for the model. And then we apply the algorithm, our instructions, to find those statistical correlations and probabilities in the data and patterns. By the way, machine learning is never about causation. It's always about correlation. Okay. And so in the process of applying this algorithm onto the data and learning these patterns, we actually train this model, that mathematical formula, the weights, or whatever else, depending on the approach we chose. This process is typically very iterative because we want to achieve the highest accuracy possible. And so we may try different algorithms, and sometimes we want to go and look for more data, different data. We may prepare it differently just because to get that accuracy that we want to really, differentiate those cats and dogs well. And at every point, we actually evaluate the model, and we do it on a holdout data set. So original data set, we use most of it for training, but we usually keep some of the data away from the model because that's the one we use to evaluate it. Okay. After multiple iterations of training the model and evaluating it, and by the way, data scientists will tell you that it's probably more of an art than a science. It takes a lot of intuition and experience. But once we're happy with the model, which is really just a mathematical function, typically with probabilities attached, we can then run it on new data, which the model has never seen. And it goes through the same process. We extract the feature, we prepare it in the same way as we prepared the training data set, but we now have the model which will predict, I would put some labels or predictions or whatever that model we're using and whatever we're using it for. Okay, so whether it's recognizing images, label them as cats or dogs, or maybe identifying spam or telling us the potential selling price of a house. Okay. By the way, I'm going to pause here because I also want to mention that with COVID, things have become very, very interesting when it comes to machine learning. Because the key assumption we make here when we train models and then use them for future predictions is that future data or the data which we'll be using to kind of predict is going to be very similar to the training data. Okay. And that has completely changed with COVID because human behavior has changed as a result of lockdowns and other restrictions. And what's as a result, many organizations right now are struggling because they have been a massive data shift because the new data looks very different from the historical. We don't shop the same way anymore. We don't buy the same things. We don't do the same things as we did, 6, 7 months ago. And data changes all the time. That's known as data drift, and that's why it's important to retrain your model on a periodic basis. But right now, again, it has been a massive data shift. It's not even a drift, it's a shift. Okay, and so as a result, organization experiencing an information deficit because if you have these models but you can't use them because they were trained on data, way back, and now um, your situation, your data is different. You kind of, they are right now, many of them are aggregating, accumulating enough data to be able to retrain the models. Okay, that was a bit of a segue, but kind of going back to the to my presentation, if all of that, what I've just described, sounds to you like magic, well, I'm not surprised because it's a complex field, and like Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic. But what I'm hoping I have convinced you, so far, is that it's really not magic. Machine learning and AI, because it relies on machine learning, is um, really mathematics. It's really statistics that identify historical patterns in data or patterns in historical data to predict something that we'd like to know from those correlations. Okay. Now, remember this slide? John McCarthy and his friends, and when they set out simulating human intelligence, which was arguably a very ambitious endeavor. Instead, like I've been telling you, we ended up with something that is more mathematics or statistics on steroid and which has absolutely no intelligence in it. So, and we are nowhere near, by the way, replicating human intelligence. So what's going on and why did we land where we are? And, what is it like this current AI? Well, some people say that maybe we're just thinking about AI in the wrong way because does anybody know what this image is? Some of you are probably nodding heads and saying, yeah, this is one of the first attempts to fly by the Wright brothers and their partner, Dan Tate. And why am I bringing this up? What's the connection to artificial intelligence? Well, quite simply, it's like with the human desire to fly like birds, we actually, have something more like this. Okay. And similarly, with artificial intelligence, we want this. We got the planes, or actually maybe more like that plane. And two prominent researchers in the field, Peter Norvig and Stuart Russell, said that airplanes don't flap wings. So why should computers think? Now, they also said that the quest for artificial flight, succeeded when the Wright brothers and others stopped imitating birds and started learning about aerodynamics. Actually, the field of aerodynamics emerged after the first planes were built, interestingly enough. And so when it comes to artificial intelligence, maybe AI, at least the current incarnation of AI is really not about simulating human intelligence. It's really maybe something different, something new. And to push this analogy further, we actually building that AI plane while trying to fly it. But what does AI mean in the context of the business? Well, the key word here is support. I think of it as data-enabled, automated, adaptive decision support system, right? It's really not about replacing human intelligence. It's more about augmenting it. And there are probably three key areas and three use cases, broad use cases for the current, again, incarnational state of artificial intelligence. So one of them is artificial intelligence as artificial perception. It's really about having these algorithms kind of running in the background as a constant process and surfacing, sensing and percepting and surfacing the changes and patterns and variation and kind of surfacing them then to the human attention so people can act on that. Similarly to kind of what the brain does, the subconscious brain. The second one is about, like I just mentioned, is about supporting humans in decision making. Because machines are really better suited to making some decisions and some in a space that involves, let's say, a large number of dimensions in the data, input dimensions, or when it comes to big data, analyzing it very quickly. Or maybe when the interaction between different variables are complex. Humans, on the other hand, are exceptionally good at making predictions when data is not available, when it's limited, when we need rely on analogy or things like causal inference or judgment. Because again, machine learning, AI, still not able to uncover any causality or inference. All they can do is uncover correlation, statistical correlation, and patterns. Okay, and so what we're seeing right now is many approaches to taking those AI machine learning capabilities and augment human decision-making process. And I would actually also caution you if you're thinking about automating some of the decision-making process, that could be a bit of a dangerous path forward because of just for the reasons that I described, because humans and machine, there's no intelligence in machine intelligence and artificial intelligence. And humans are still much better at making certain types of decisions. So what really should be looking at is complementarity here, empowering people, supporting them, sort of combining this machine and human intelligence. I'm probably going to skip this slide about automation because you probably have read a lot of it in the news. Automating AI is automating many processes across industries and automating away multiple occupations like radiologists and teachers and reporters and what have you. Yeah, some of it is happening, but again, I caution you to not fully automate away occupation or processes because there are always edge cases. There are always situations where machines may not be able to make the optimal decisions because they are biased, because of the way how they've been built and sort of design decision and trade-offs that were made during the whole design and building of a particular application. But where AI is helpful is again in augmenting human capacity and capabilities, for example, in decision making. And so some people talk about, for example, the third way of business transformation, where the previous ones were about more standardization of processes, and more recent one, sort of 50, 20 years ago, were about automating them. Right now, what we're looking at creating more adaptive processes where humans and machine can work side by side, and complement each other to achieve that, those flexible, faster, and more adaptive behaviors and decisions. But at the same time, rely on humans for some critical ones, for edge cases, exceptions, and so forth, or at least maybe having people as a mechanism for a course or the override, sort of keeping humans either in the loop or over the loop. Okay. I think I'm probably at my time, and I want to pause here, maybe open up for question. But the key takeaway I do want to take you from this presentation is, and I'm hoping I've convinced you that there is no intelligence in artificial intelligence, and it's really um, about machine learning. It's really about mathematics and statistics on steroids, kind of using historical patterns in the data to predict future outcomes, as long as the data we're using for predictions is similar to the historical data on which the machine has been trained. So when you think about that, I urge you to exercise caution because, again, of these, of what AI is. All right. I'm going to stop here. Pam, over to you. I don't know if you have any time for questions. I'm happy to take a few.
Yes, yes, we do. But we're going to go ahead and stop the recording.
Okay.
So